So in previous videos, we already looked at query planning, and we had already situations like the one shown on the left. Here we have a SQL query, select B, C from T, where A equals 8 and B equals 5. So a very simple query, just one table is being accessed. And we could show this in relational algebra as follows. Here we have T that is accessing the table. Then we have the two selection operations, and then there's a projection. Of course, you can swap the two, you can combine them. We had all of that in previous videos. This is one possible visualization, one possible way of expressing this query in relational algebra. Well, but then the question occurs, how would we do that in a column store? Because a fundamental difference we have in a column store is that the different attributes belonging to the table do not exist in the same structure. So in a row store, we have one structure where all the attributes live in that structure. In the column store, that is not the case. So actually what we have in a column store is something like that. We have different columns, one column for each attribute. So it may look like this. We have an A column, a B column, and a C column. So in order to process this plan, we could do something like this. We say, okay, we first join all of the attribute values into what looks like a row layout. So here still we have arrays with one entry each. This is basically an array of B values. Here we have an array of A values, and here we have an array of C values. So after this join, we have something like this. We have an array of a struct. So we have three different attributes here, and then here we have A, here we have B, here we have C. So basically we combined the three columns into a row layout with three attributes. And then we do all of this, and we filter, then we project, and so forth. So this is transforming the original data layout. The data layout, which here is still in column layout, is then here transformed into a row layout. That is one extreme way of doing this, and this is called early materialization. You have all of this for free in a row store. If you remember back in a row store, if T is represented in row layout, you don't have to do any of this. We can draw a box around this here. So nothing of this has to be done at query time. You don't have to perform a join over different columns. The different attributes already exist in row layout in this store. So basically the box you have here is the same box here in a way. It's the same thing, kind of. You don't have to do anything. You get this layout here, this row layout, for free. You do not get it for free in the column layout though. And therefore it makes a lot of sense to think about whether we should actually run this join at query time or not, because it may be very expensive. So let's look at that in more detail. So there's another option you can do in this situation, and that is the following. This is late materialization, at least partially. So what we do is we push down the projections. So the projections are pushed down as far as possible, as in standard relational rule-based optimization. So we first filter out all values having this specific value. Then we project to the row ID. So what this means is we obtain a set of row IDs having this value. However that set is represented here, that doesn't matter for the moment. We will get back to that in a moment. But logically, we just fetch the rows here from this A column where A is set to 8. We do the same for B here, but project to B, row ID. So here we also keep the values of B because we need to project to that later on. Here we only keep the row ID. We throw away this A value, which happens to be 8 anyway in all of the cases. So here already there's a difference. What happens above then is a join with respect to row ID. So this is a natural join on row ID. And only after that we fetch the corresponding values of the C column. So you see here C is only joined to after this join has been performed. And this might have the effect that here we have potentially few results. In the optimal case, we only have to fetch very few attribute values here. We don't have to take all of the C column, all of the values that live in the C column. So ideally, very few values are produced by this join, and then only for those few values we have to fetch the corresponding value of the C column. And this is an example of late materialization. Only at a very late stage in query planning we fetch the values of C. And you could actually visualize it as this. So I'm using the term anti-projection here because it's really the inverse operation to the projection. What we do here is we extend the internal schema being used here. Here internally the schema is only B and row ID. That is the schema that is produced by this operator here. So we have a schema of B and row ID. Here the schema is row ID C. And then after this join, we can project to BC again. So after the join, we have the schema row ID, B, C, and then we project this to BC again. But what happens here logically is that this schema, this internal schema, is extended by C. If you read it from the left here, you add another attribute. And that is the reason why I call this an anti-projection. This is an anti-projection. And another term that's used for that is tuple reconstruction, tuple reconstruction joins. That is the implementation, but on a high level, on a logical level, in terms of relational algebra, this should be called an anti-projection. So this is a partially late materialization. You could also do it fully late. That is shown here. So what happens here? Again, it's another valid translation of this query shown on the left. We have our input columns here, A, B, and C. But the important change here is here we do not keep the values of B. Again, as on the A column, we also project to row ID. So if we go back, here we kept B and row ID. Now we only keep the row ID. Then basically this join degenerates to an intersection. When we intersect, this gives us the result of the conjunct. Basically that is this expression here that is produced here. So this is A equals 8 and B equals 5. So this intersection produces the row IDs where this holds, and then here it goes into this operation. Here I allow for an operation having more than 2 inputs. So basically what you do is you take this list of row IDs produced on the left side. Those are the tuples you're interested in. But now you have to project to those attribute values, which means you anti-project again. But now you anti-project for 2 attribute values. You have to take the row IDs and find their corresponding B and C values. However that is implemented, logically what you do is you go back to this B column, you go back to the C column, and then you end up with B and C. So the B and C values of rows having that condition. So here again, it could be considered an anti-projection. That is what late materialization is about. And this may have quite a performance effect in column stores. So you should consider that when handling large data volumes in the column store. Again, here's this high-level view on it. Standard projection does something like that. If your relation looks like that, you have 3 columns, A, B, and C. You project them. And usually projection can only make the schema smaller. It can keep the schema, of course. If you had A, B, C, then we would have the same thing as shown on the left. But here we throw away one of the columns and then we end up with a schema like that. Anti-projection is doing the inverse operation. So if we take this schema and we want to append another attribute that doesn't exist yet here, then we could do something like this and we end up with the original schema. So in the projection, the question is when to narrow the tuples. In anti-projection, the question is when to widen tuples. So let's look at a more concrete example in the column store. Let's make the query even simpler. Let's assume it's a simple select star from T. So how would you do that in the column store? So if you have a column layout, you have 3 different structures for the 3 attributes, assuming that T only has those 3 attributes. And the question then is, when do you actually form those rows? When do you construct rows? So here If it's only 3 rows distributed over those columns, the question is, when do you form those rows while executing the query? That is what tuple construction or anti-projection is about. So let's look at one possible way of implementing that. Here again, I added the filter condition. So what you do here is you send this to the column store. It has it represented in 3 different structures. And then eventually what you might do is you materialize it early, which means you early on form a row layout. Of course, only containing the stuff you need at some point in time. If T had more attributes, it's not necessary to also include D, but at least the columns that are required eventually in the plan are put into a column layout. And then here, in an extreme case, you could only after forming the row layout, you execute the filter condition, you do the projection, and then you end up with something like that. That is one way of implementing early materialization, by really first joining the necessary columns into a row layout, and then you do all the other operations. So very similar to the example we had before, if you go back. So this is basically what is shown in this implementation here. You first join them into a row layout, and then you do all of those operations, which is not the most efficient thing you can do here. So let's look at a more interesting case. Let's look at late materialization. How could you do that? So one way of doing that is to say, okay, I don't form any row layout based on this, but what I do first is you look at the individual columns, and basically what you do is you keep a bit vector marking the qualifying entries. So basically here, this is a matter of labeling. Here you label the individual rows, whether they are interesting with respect to a filter condition. So here in column A, rows 1 and 2, here if you start counting by 0, 0, 1, 2, rows 1 and 2 should be labeled with a true, with a 1. This is a bit list signaling whether in this column A equals 8. You do the same for the B column. Here we're interested in rows having B equal 5, so that would be this one only, so it must be 0, 1, 0. Then of course you can combine the two results. We are interested in an AND, and then you end up with this, only this row is labeled. So this already tells you the rows that have to be processed further on. This bit list signals this is an interesting row, this is not interesting. I don't have to look at any data with respect to this row. I don't have to look at any data with respect to that row. That is what this is saying. Only the stuff in the middle is interesting. So what we do in the next step, here again, this is a bit list shown on the previous slide. Here, that's the same bit list. This conjunction bit vector, it's the same thing shown here. Now what happens is I have to fetch those values here. I have to fetch the 5 of the B column and the 3 of the C column. Let's mark it. That is what I have to fetch, and that can be done by joining the 3 structures, be it in one step, be it in multiple steps. Whatever is the most efficient way of doing this. But logically, again, what you do is you fetch this value of column B, you fetch this value of column C. This may be still in separate structures, maybe still something like a column layout, but it may also be a row layout. Here in this slide, what you do is you keep it in separate structures. So this could, of course, have more results. Assume you had also here a 1. Assume if this is also 1, then you would also fetch the 2, write it down here, and fetch the 9, write it down here, and then only afterwards you materialize it into a row layout. So this is an example of late materialization. This idea of late materialization also applies in join processing. So let's look at another example where a join of 2 relations is being processed. This is a SQL query. So what we're interested in here is the join of T and S over the A attribute, so natural join over that, if there aren't any other columns that have the same name. But that is the case here. So that's a natural join of T and S, and then we project to B and C. So what is typically done in early materialization is you join the 2 relations, and then you end up with something like that. So here you have the join column and the other 2 columns, B pertaining to T, C pertaining to S. And then comes the projection. That would be one way of implementing that. Here you project to B and C after the join. You can't project any earlier here, of course, because A is required in order to be able to perform the join. You need the A column here and here in order to understand which tuples belong together, which pairs of tuples have to be formed by the join. So this is how early materialization would perform the join. How would that look like in late materialization? Well, in late materialization, in order to process the same join, what we could actually do is something like that. We just look at those columns, assuming we have a column layout again. Here we have the row IDs from 0 to 5 on both sides. And then what we do in the join is we do not project to any data, but we just inspect the A columns. In an equijoin, we know that this is the result. We know that this is the result, and we know that this is the result. That's it. Yeah? 4 doesn't match, 7 doesn't match anything. Yeah, that's it. Only 3 tuples, and we can keep that information in a structure that's called a join index. That's what's being computed here. So basically here we have pairs of row IDs. So this means in relation A, tuple with row ID 0 matches tuple with row ID 1 in relation S. That is what is shown by this edge. Those 2 tuples match, and therefore we found a join result here. The same holds for these two tuples. So here we had a 2. This 2 matches this first tuple here. So we have an entry 4, 0. That's this one, and another is 5, 0. This is just keeping the information which tuples have to be joined. So tuple with row ID 0 joins tuple with row ID 1, tuple with row ID 4 joins tuple with row ID 0, and so forth. So here we're not projecting to any actual attribute of the table. We just keep the join information with respect to the row IDs, this artificial row ID, which is a physical implementation structure, which has nothing to do with the actual attributes, of course. So, and now what needs to be done after the join is, because now we found out what is the result, we still have to join it. So we want to have the same result as an early materialization, and that means is we do something like an anti-projection again. For those tuples, we have to fetch the corresponding values. For this row ID, we have to fetch the B column. That is what is displayed here. For this row ID, we have to fetch the C column of S. That is what is displayed here. So that we end up with a result like that. And that is what happens here. So we here introduce this anti-projection saying, okay, now we perform joins, tuple reconstruction joins in order to fetch the attribute values. And afterwards, of course, we should get rid of the row ID. The row ID is not something we should send to the output. Therefore, there's another projection here, removing the row ID. That is why we have an actual projection here after that anti-projection. So in the end, we end up with this result, which is the same result as shown above in early materialization. So you see, this is an interesting technique. Late materialization is an important technique in that it may make a difference, especially in the column store. You may also use it for row stores in some situations, but especially in column stores, which are usually used in main memory database systems, they make a huge difference. So let's look at the pros and cons. Advantages of early materialization are there's no re-access of columns necessary. You could also see it as a bottom-up way. So when you have your plan and you do whatever in this plan, let's say whatever, what you do is when you fill in the data here, you keep all the attributes you ever need further up in the plan. So if you know eventually here you need an A, and eventually here you need a D, and here you need a B, then you know, okay, I have to make sure that I input it already here at the leaves of my plan. You input A, D, and B and make sure that all the information reaches this operation here. So you fill it in bottom up. And those plans are somewhat easier in a way because they're very textbook style. You don't have to worry about these additional anti-projections. Disadvantages are possibly you might generate very wide intermediate results. So if you go back to this example, if you fill in all those column values already early on and then later on you only look at very few of those values, well then why did you read it in the first place? So you might be reading a lot of data here. You might be reading all of the columns entries even though later on you discard most of it. So that's not the most efficient way of doing that. So in late materialization, the advantages are you construct the tuples only when necessary. That's a big advantage of that method. However, it involves also some slightly more complex planning. So these anti-projections are basically translated into tuple reconstruction joints. But at the end of the day, you have more join operations in your plan, which means you have a bigger search space in terms of which join is executed first. So you could say on a high level, so if you look at what you have in a standard row layout, assume you have a relation R, there's a couple of attributes, and you have a relation S that has a couple of attributes, and then you join them. What are the options? You can decide whether you put R on the left side or S on the left side. You can decide which physical join algorithm to use. Those are the options if you're talking about a row layout. Okay, so in column layout, if you have relations R and relations S, well actually those relations contain like sub-relations. Yeah? If we had attributes A, B, C here, they all live in the same structure. Let's assume it's D, E, F here. They're all part of the same structure. However, if it's in column layout, we have different substructures for that. So just for R, we have, if you wish, 3 tables. We have an A table, we have a B table, and we have a C table. And they are separate structures, even though, of course, logically they contain the same rows. And what this means is, what we are deciding upon during query processing, during query planning, when using late materialization is when to execute those joins. So we make the join order problem more complex by introducing more tables. As we now not only have one table per relation, we have one table per attribute of each relation. We make decisions on when to join which pairs of attributes, how to come up with the right join order. That is a decision in late materialization, and therefore the entire process, of course, is way more complex. You have way more options and a bigger search space. Yeah, disadvantages is also here that you might be re-accessing columns. We had an example of that above. Here, this was an example for re-accessing column B. So we use it in the first round to fetch the row IDs of qualifying tuples that happened here. But then when fetching the attribute values in this tuple reconstruction join here, we have to go back to this column. Of course, this only makes sense if you are able to selectively, to randomly access the individual values. If you scan it here again, you don't gain so much. But at the end of the day, you go back to the values of B. And that is why you have an extra edge here in this graph. Now this plan is not a tree anymore, it's really a directed acyclic graph. So this might happen, that you re-access those data values. So bottom line, late materialization is a technique you should be aware of when implementing column stores. As a relation in a column layout or even in vertical partitioned layout is split into multiple structures, not a single structure as in row layout, it may make sense to worry about questions like when should I fetch the actual attribute values? Should I do it early on or should I do it at a later point in time? So this has the effect that the search space of our join orders is increased because we introduce more structures, more input relations in query planning. But it may have the effect that the query becomes faster, as we may end up with situations where we only fetch few attribute values. If you fetched multiple values here, assume many tuples qualify, you still have to go back to reading column B again, you may again end up with a plan that is slower. So it's a very similar problem to index selection in a way. We had the effect when looking at unclustered index, you have to be careful. If the selectivity is high, if only few tuples qualify, then late materialization makes a lot of sense. For a higher number of tuples, you should be careful. So again, it's a decision a cost-based optimizer should take to come up with a better plan, but not with a plan that is worse. If you liked this video, don't forget to hit the like button. Thank you. So if you want to see more database videos, be it in English or in German, take a look at my website datenbankenlernen.de. It has a couple of English and German videos. You can also subscribe to my YouTube channel, Jens did, or you look at our website infosys.uni-saarland.de. See you there!